Hi everyone, I'm Gemma Catolino, postdoctoral research from Delft University of Technology, and today I'm going to present our journal first paper published at the Empirical Software Engineering Journal that had the goal to improve change prediction models with code-smell related information. So, as you know, during the evolution of software, change is unavoidable. So, know in advance the code elements that exhibit a higher change proneness is crucial for developers. And in the past, a lot of effort was spent by the research community and in particular for provide change prediction models. And also in our recent studies, we conjecture that developer-related factors can be a useful source of information to predict classes more likely to be changed in the future. For this reason, we took into account three bug prediction models that exploited developer-related information, and we applied to change prediction contexts. What we discovered was that model using bug prediction worked well also in change prediction contexts, that the performance increased compared to the baseline of change prediction models, and we noticed that high complementarity between the factors. But according to a previous study of Com et al. That discovered how code smell can impact change and fault proneness of a code component, we conjecture that the addition of a measure of code smell severity could improve the performance of existing change prediction models. In order to compute the severity of a code smell, there is J-code odor tool. In particular, this tool detects 6 code smell types using structural metrics and normalizes the distribution of such metric values in the interval between 1 and 10. In the context of our study, we relied on two datasets that we joined together. In particular, this dataset of Iurescu and Madeschi and Palumbo et al. Consisted of 41 releases of 14 projects, and inside there were the value of intensity index, anti-pattern metrics, structural metrics, and developer-related factors. We needed to include, so we computed additional metrics related to change from baseline models, and in this way we had our independent variables. In order to have our dependent variable, we computed change from classes, so the oracle of our model, using change distiller tool. In order to construct our model, so based on 5 different models, so one related to structural metrics, one related to process metrics, and 3 related to developer-related factor, the models that I showed you before, we added for each of them the intensity index and the anti-pattern metrics. In particular, for each model, we constructed one model only for structural metrics. This is an example. Structural metrics plus intensity and structural metrics plus anti-pattern. So we did this for each of them. And finally, we run the model using logistic regression classifier and 10 cross-fault validation as a validation strategy. The first results that we obtained was that developer metrics together with the intensity index perform well. So the model that include this factor performed well compared to the other. But of course, we notice also high complementarity. And for this reason, we put all these factors together. We applied feature selection technique, and then we rerun the model, logistic regression, and 10 cross-fault validation. What we discovered was that, according to what I said before, that developer-related models together with intensity metric work better than baseline, and combined model that includes all the factors post the performance up to 20% in terms of F measure compared to the other models. Thank you for listening, and see you live for ICSI 2020.